Hello everyone, welcome to the topic analysis of pure C circuit, that is pure capacitor circuit. So in previous lectures we had discussed about the analysis of the pure resistive circuit and pure inductive circuit. In case of the pure resistive circuit, we know that the both current and voltages were in phase, and in case of inductive circuit, current used to lag by an angle of 90 degree with respect to voltage. Let us see what will be the nature of current in case of the pure capacitive circuit, and as well let us draw the waveforms, phasor diagrams, and let us calculate the power consumed also. In case of the resistive circuit, the power consumed is Vrms into Irms, and in case of inductor circuit, the power consumed is 0. Let us calculate the power consumed in pure capacitor. So to start with, let us consider a pure capacitor. Pure capacitor is connected to the sinusoidal voltage V, that is V is equal to Vm sin omega t. The capacitance of this capacitor is C. So whenever we apply the voltage to a capacitor, the current starts flowing and the charges gets accumulated on the capacitor plates. So which is given by the charges Q. We know this already. Charges Q is equal to the capacitance of the capacitor into the applied voltage V. So Q equal to C into V. So and the current flowing through the capacitor, which is I equal to the rate of change of charges dq by dt, rate of change of charges, that is dq by dt. So let us substitute dq here, and we know that q equal to cv. V is nothing but the applied voltage, that is Vm sin omega t. So upon substituting, we get I is equal to we need to differentiate the charges with respect to the time. So q is nothing but it is C into V, it is C. V is nothing but Vm sin omega t. So we need to differentiate the C Vm sin omega t with respect to t. So upon differentiating this, let us take out C and Vm since both are constant. Here we are differentiating with respect to only t. So differentiation of sin omega t will be cos omega t into constant omega. Omega is constant here. So this can be written as omega c into Vm cos omega t. Now let us convert this cos omega t into sin omega t to compare the voltage and current waveform. Since voltage is sinusoidal, let us convert this current also in sinusoidal form. So this can be written as I is equal to Vm. This omega c can be written as 1 by omega c in the denominator. So cos omega t in terms of sin, we can write it as sin omega t plus pi by 2. In case of inductor, this was minus pi by 2, but here it is plus pi by 2. So this can be written as I is equal to Im sin omega t plus pi by 2. So this is the nature of current in case of the pure inductor. Whenever we apply a sinusoidal voltage, the nature of current will be I is equal to Im sin omega t plus pi by 2, where Im is equal to Vm by Xc, where Xc is the capacitive reactance which is given by 1 by omega c. Xc is the capacitive reactance which is equivalent to the resistance, the equivalent resistance of the given capacitive circuit is the capacitive reactance Xc. So by comparing the voltage and current waveforms, we can say that our current wave, it is leading by an angle of 90 degree. Since it has plus sign, plus pi by 2, which means the current wave starts 90 degree before the voltage wave starts, which means the current is leading here. Current is leading by an angle of 90 degree. So let us draw the phasor diagram. The phasor diagram. Phasor diagram with respect, let us consider again voltage as a reference V, and current leads here. Current leads by an angle of 90 degree, that is pi by 2. It is plus pi by 2. So plus pi by 2 will be first quadrant. So it is I. So which means current leads the voltage by an angle of 90 degree. Or if you write with respect to current, voltage lags. Here with respect to current, voltage lags by an angle of 90 degree with respect to current. Voltage lags. With respect to voltage, current leads. Let us indicate this in the waveform. Considering voltage as the reference. It is varying with respect to omega t. Let us draw the current. So since, as I said earlier, the current is leading by 90 degree, which means current is starting before the start of the voltage wave. So this is 0, this is 90 degree, pi by 2, this is pi, this is 2 pi. So to draw pi by 2, let us, the easiest way is, we know V is equal to Vm sin omega t, I is equal to Im sin omega t plus pi by 2. Easiest way to draw the waveforms is, we just substitute the omega t different values. So first substitute omega t is equal to 0. Omega t is equal to 0 means sin 0 will be 0. So this is instant. Omega t is equal to 0, right? So at omega t is equal to 0, at this instant, voltage is 0. Your current is Im sin omega t plus pi by 2. So omega t is 0 means it will be sin 90. Sin 90 is 1. So 1 into Im is Im. So at omega t is equal to 0th instant, our current will have maximum value. This is Im. This is voltage maximum Vm. At omega t is equal to, let us substitute 90 degree. So V is equal to Vm sin 90. Sin 90 is 1. So at 90 degree, your voltage will be having maximum value Vm. Current sin 90 plus 90 will be sin 180. Sin 180 is 0. So at sin omega t is equal to 90 degree, at this instant, the current becomes 0, which means current becomes 0. So this waveforms follows, or we can draw in another way, which means you need to start the current wave 90 degrees before the voltage. Here voltage is starting, it is 90 degrees before the minus 90 degree. Before the start of the voltage wave, current is starting. So this again continues. So this also vice versa to the inductive circuit. So similar to the inductive circuit, whenever voltage is 0, current is maximum. Whenever current is 0, voltage is maximum. So this is the nature of the current. This is the current I, this is voltage V, applied voltage V. This is the waveform for voltage and current. Now let us calculate the instantaneous power and as well as the average power. First let us calculate instantaneous power. Instantaneous power is given by P is equal to V into I. So this will be Vm sin omega t into Im sin omega t plus pi by 2, omega t plus pi by 2. So this can be written as omega sin omega t plus pi by 2 is cos omega t. So this can be rewritten as Vm Im sin omega t into cos omega t. Applying the trigonometric formula again, sin theta into cos theta is equal to sin 2 theta by 2. So that is Vm Im by 2 into sin 2 omega t. So this is the instantaneous power in the pure capacitive circuit. So here also we can observe there is no constant term, fixed term. It is also variable with respect to 2 times of the normal frequency. 2 times of the normal frequency. Let us indicate this in the waveform. Before that, let us calculate the average power. Average power we know it is indicated by capital letter. Average power for a one complete cycle. Length is 0 to limits are 0 to 25. Length is base is 1 by 25. We need to integrate the instantaneous power with respect to omega t. We will get the average power. So this will be 1 by 25 integration of 0 to 25 Vm Im by 2 sin 2 omega t with respect to, we need to differentiate with respect to d omega t. So upon differentiating and substituting the limits from 0 to 25, we will get this as 0 again 0. So from this we can say that the power consumed by the average power consumed by the pure capacitive circuit is 0. Consumed or power absorbed by the pure inductive circuit is 0. So we can conclude that all the 3 elements, resistor, inductor and capacitor, only the resistive element's power, resistive element consumes the power which absorbs the power. The remaining passive elements, that is inductor and capacitor, does not consume any power in the electrical circuit. Let us draw the waveform for power. Waveform for power. Let us take voltage as the reference. This is the voltage, and we know the nature of current already. Whenever voltage is maximum, current will be 0. Whenever current is maximum, voltage is 0. So this is the nature of current. This is the current I. Current I. Now we need to draw the power waveform. Here we are drawing voltage, current and instantaneous power P. We know power is V into I, voltage into current. We have voltage and current waveform. We just need to multiply both the waveforms. So first let us look at starting point. Here voltage is 0, current is maximum. So 0 into anything is 0. So your power wave starts from here. Again voltage is increasing in positive manner, current is decreasing in positive manner. So positive into positive, if you multiply, it will be positive power only. So at this instant current is 0, so power should be 0. At this instant again voltage is 0, power should be 0. Here power should be 0, here power should be 0. Here also again power should be 0. At this instant, whenever voltage or current is 0, power should be 0, because 0 into anything is 0. So between 0 to 90 degree, both are positive. So multiplication of positive into positive will be, you will get positive of, in the 90 to 180 degree, voltage is positive, current is negative. So positive into negative is negative, we will get negative of, here both are negative, negative into negative, we will get again positive, positive into negative, negative of, positive into positive, positive of. So this keeps on continuous. So this is the positive of, negative of, positive of, negative of, positive of. So here also this fluctuates 2 times of the normal frequency. So for one cycle of voltage, instantaneous power is fluctuating 2 times. There are 2 cycles of instantaneous power. This is instantaneous power, and the peak value, this peak value is Vm Im by 2. So this is about the analysis of the pure capacitive circuit. So one thing we need to understand from these 3 analysis of inductor, resistor, inductor and pure capacitors. In case of the resistor, both current and voltages are in phase. In case of the inductor, current lags the voltage by 90 degree. In case of capacitor, current leads the voltage by 90 degree. And power consumed in all 3. In resistor it is Vrms into Irms. In inductor and capacitor it is 0. So inductor and capacitor does not consume any power in electrical circuits. The only element which consumes power in electrical circuit is resistor. Thank you.